we're going to do something a little different today. We are not going to find the instantaneous rate of change at a specific spot. We're just going to find the formula to find the slope at any spot. So originally, this is the formula we got for the instantaneous rate of change. And we talked about how this is actually the formula for the derivative. Okay, so the derivative is this. Normally what we would do is we would say, hey, for this function, like 1 over x, we would say find instant rate of change, or find the slope, or find the derivative at x equals something. So instead of doing that, we are just going to say find the slope equation. And one other way to say the slope equation is the derivative function. So what we do here is we follow this formula right here, but we don't actually plug in a number for x yet. We wait. So let's do this here. For this example, we're still doing the derivative formula, but we're just not going to commit to any one x value. We're just going to leave x in there. And so if I plug x plus h into my function, I'm going to get 1 over x plus h minus, if I put x in, it's just going to be 1 over x all over h. Now I want to simplify this down, and I want to take the limit so that all I'm left over is x. So next I would do 1 over h, and I like rewriting it like this so that it's not a complex fraction. Next step, I'm going to find common denominators. So on the right side, I got to multiply by x plus h on top and on bottom. On the left side, I got to multiply by x on top and on bottom. It would look something like this. Okay, now we can actually combine the fractions. We just have to be careful. This is the most common thing missed when we're doing these slope functions, these derivatives. You got to distribute this negative. That's important because x minus x will cancel, but then you're going to have a minus h left over. So let's write that here. Now your common denominator will be this, and you'll notice that the h's cancel. So we have canceling, but we're going to be left with a negative 1 on top, and then x times x plus h here. At this point, we're going to let h equal 0 because we've removed the discontinuity. If we had plugged 0 back in here, we would have gotten 0 over 0, which is a hole, or a removable discontinuity. But now we're just going to plug 0 in because we don't have that issue anymore. If we do that, we have negative 1 all over, and it'll just be x times x, which is x squared. So here's why we like the slope function. If I ever need to find a tangent line, I can use this right here to get the point. Then I can plug in the x value and get the slope anywhere I want. I don't have to keep doing this limit over and over and over. So the slope at 2 would be negative 1/4. Alright, we need to do another example. Let's say that our function instead was 3x squared. So I'd like you to pause the video and give this a try. Follow what I did, and then see if you can't get it. Alright, and now I'll begin doing it myself. So we're still doing the limit as h goes to 0. We're still going to be doing f of x plus h minus f of x. And so right here I have x plus h squared minus 3x squared all over h. Okay, I'm going to expand this right here. So we have 3 times x squared plus 2hx plus h squared minus 3x squared. Now if I distribute here, you'll notice I'll get a 3x squared here, which would cancel with this one. So I have actually 3 times, that would be 6hx left over, plus 3h squared all over h. And at this point, we can do what I call the butterfly. The h's divide out, and we have 6x plus 3h. Now we've gotten rid of the issue where if we plug in 0, we'd get 0 over 0. We've removed the removable discontinuity. So if h is 0, this would just be 6x. So if you ever need the slope on 3x squared, you can plug in the x value and that will just automatically give you the slope. So one thing to be careful about, sometimes your functions have more than one part and it's easy to get tripped up with all of the x's. I'm just going to set this one up and then start it. We'd still do the limit as h goes to 0. Now when we plug in x plus h, we have to plug it in twice here. So this will be x plus h squared minus x plus h in parentheses. So first off, you'll notice the negative here will be distributed here, and x plus h is twice. Be careful about that. Now, that was x plus h. We're going to have to subtract the function with just x put in, no h. So that'd be x squared minus x. Now you can see that there's lots of negatives, and you have to write the function twice. And when you plug in x plus h, a lot of people forget that second x plus h, so be careful about these little details. So the next thing you'd have to do then, and you should give this a shot, you have to expand out x plus h squared. You have to distribute your negative, and then here you have to distribute your negative again. So if you want to keep trying, go ahead. Your derivative function is going to be this, but make sure that you could get there yourself by following through on the limit that we just started.